Using an EMG signal to control an adept robot.
Rest is at 0 angle, and as I flex a little bit, should go up to the first position, flex a little more, second position, and flex all the way to the third position. It'd be possible to do more states, but it'd take probably more training to get used to your muscles holding a constant position. These are the two electrodes that measure the surface EMG signal. In the circuitry, it measures the difference between these two electrodes relative to this ground potential electrode. I'm using MATLAB to do the real-time classification of the EMG signal. I'm also showing the raw signal. As you flex, you can see it goes up. This is the estimated force and every 100 millisecond block of data, and this is the bend force. This is the LCD screen that shows the force, estimated force, and the level of contraction. As you flex, it goes up and moves the levels. I'm holding a 5-pound weight at an isometric contraction, meaning I'm just holding it 90 degrees, holding it still. And you can see the force is roughly 5 pounds, but it jumps around a little bit. At 10 pounds, you can see it goes up roughly 10. And at 25 pounds, it's around 25 pounds, maybe a little bit higher. This is based on just one set of training data, though. More training data would probably give a better estimate. This is the conditioning circuit. It amplifies, filters, and rectifies the raw EMG signal before sending to the A to D converter. So on this board, it goes to a PIC microcontroller, which has the onboard A to D. It then sends that digitized signal to the computer. The computer estimates the force based on 100 millisecond blocks of data. So every 100 milliseconds, an estimated force is sent back out to the computer to another PIC microcontroller, which displays the estimated force and the bend value on this LCD screen, and sends a number 0 through 4 to the parallel port on the adept robot, which then moves the robot to the corresponding position. This is the signal conditioning circuit. It's mostly op amps for the 3 op amp instrumentation amplifier, the high-pass filter, the low-pass filter, and the precision full-wave rectifier. There's also a balance potentiometer that balances the resistors in the instrumentation amplifier, and this adjustable gain potentiometer. This is the prototype board for the A to D conversion and the computer to robot interface. It's mostly PIC microcontrollers that do the A to D conversion and take the serial input from the computer and output it to the adept robot. This is the cable to the adept robot. This is the ribbon cable to the LCD, and there's also inputs here from the conditioning circuit. This is a PIC 16F819 that does the A to D conversion. This is a RS-232 level converting chip to do the serial communication. And this is a PIC 16F876 that receives a serial communication from the computer, outputs the information on the LCD, and also outputs the parallel estimated level to the adept robot. This is the adept robot program that reads the parallel port, determines what the value is, and moves the robot to a corresponding angle.